Good afternoon, pre-calculus class. We're going to have a great time today, and hopefully Lisa is going to be there to help out if you need any help. So, without further ado, let's get started. We have a few topics to take care of today. So the first thing I want to do is I want us to be able to evaluate logs using the inverse property. But before we get to evaluating, we want to make sure that we understand what the inverse property is all about. So let's take a look at log base 10 of 100. And we all know from our most recent experiences that is equal to 2. And there's another way for us to write log base 10 of 100, and we could write it as log base 10 of 10 to the second, because 100 and 10 to the second are the same thing. And you'll notice that the answer to this, of course, will also be 2, because either way we're taking the log base 10 of 100. And now you can see that the 2, that's the answer, is actually also in the exponent. So what we have going on here is we have log base 10 and 10 to the, and what we find is they actually kind of cancel each other out because they are inverses of each other. Log base 10 is a log function, 10 to the 2 is an exponential function, and log functions and exponential functions are inverses of each other. So log base 10 and 10 to the 2 cancel each other out, and so we're left with just 2. So we're using the inverse function there. So I'm going to write down that logs and exponential functions are inverses. And quote-unquote, cancel each other out. And so that's the rule that we're going to use when we are solving the next few problems, and these problems are really simple. So let's go down to evaluate. And so we're going to evaluate the first one here, where it says log base 5 of 5 to the 7th. Well, we just talked about this, that log base 5 and 5 to the cancel each other out, so log base 5 of 5 to the 7th is just 7. Couldn't get any simpler than that. And let's try the same trick down here. And here we see it again just in a different form. We see 7 to the log base 7, and again, these two things are canceling each other out because they're inverses of each other, just like x squared and square root. When we take the square root of x squared, we just get x. So 7 to the log base 7 of 8 is, you guessed it, just 8. Again, it couldn't get any simpler than that. And then we move down a little bit, and we see that we have natural log. Well, of course, we know that the natural log is really nothing more than log base e. So really, we could think of this as log base e of e to the 4th. Well, again, log base e and e to the cancel each other off, so the answer is just simply 4. Using the inverse property again, log base e and e to the cancel each other off. And the last one here, natural log of the cube root of e squared. Now, this one's going to take a little rearranging before we can actually evaluate the log, and so we use our knowledge of cube roots, and remember that the root goes in the bottom and the power goes in the top. And so what we really have then is the natural log of e to the 2/3. Remember, the root goes in the bottom, just like in the trees. And then again, we have the natural log, and we have e to the, and they cancel each other off. So our answer is just simply 2/3. Again, couldn't get any easier than that. And let's go down a little further, down to e. And again, we have to do a little rearranging here. So we have log base 5 of the 4th root of 5. And so we can, again, rewrite this slightly here. So we're going to have log base 5 of 5, and the 4th root of 5, of course, is 5 to the 1/4. Sorry, need to follow the writing with the camera. And so again, log base 5 and 5 to the cancel each other out, and we're just simply left with 1/4. Nice, easy stuff. And let's move down to our second to last example on these. We have log base 3 of 27, and we can write 27, as we all remember, I hope, as 3 to the third power. And of course we're choosing 3 because that is our base. So log base 3 of 3 to the third. And again, we have our little trick here, log base 3, 3 to the, those guys cancel each other out, and so the answer is just simply 3. That probably had too many 3's in there, but I think you probably got the point. And our last problem. Again, it's kind of similar to the previous ones, just got a little addition into it. No big deal there. So log base 2 of 2 to the, well, 2 to the first, because 2 is just 2 to the first. So log base 2 of 2 to the first is just 1. And log base 2 of 1/16, well, that's kind of something we did in the previous class. So we know that 2 to the negative fourth power is 1/16. So we have log base 2 of 2 to the negative fourth. But of course, log base 2 of 2 to the negative 4 is just negative 4. So we have 1 plus negative 4, which makes negative 3. So we are done with the first part of our lesson, which is evaluating logs using the inverse property. So we're going to go on to our next part of our lesson, which with my low-tech clipboard here, hopefully we'll be able to do some quick changeover without too much interruption. So we're going to move on now to sketching log functions. In order for us to sketch our log function, we first need to know what it looks like. And as usual, when we don't know what a function looks like, we make a little t-chart and explore it. So we're going to use our, I've already made our left side of our table here, the x part of our table, and we're just going to figure out the y's. So let's just put in the numbers and see what we get. So we're going to do log base 2 of, in this case, negative 1. And we talked about this last time. We can't do the logs of negative numbers. So log base 2 of negative 1 does not exist. Nothing there. And we move on to 0 for x. Put the x in up here. Log base 2 of 0. And again, we remember from last class that we can't take logs of 0. So that is also not going to exist. And then we move on to 1. Put that right up here. So log base 2 of 1. And we remember that log really asks the question, 2 to what power makes 1? And of course we remember that 2 to the 0 power makes 1. So when there's 1 here, the answer is 0. Y is 0. Log base 2 of 1 is 0. And then we move down to 2. Put the 2 in there. Log base 2 of 2. In fact, we just did that problem just a moment ago. Log base 2 of 2 to the first is just, well, 1. So y is 1. And then we can keep going on here and put the 4 in here. So 2 to what power makes 4? And that's obviously 2, so y must be 2. And we do the same thing with 8. 2 to what power makes 8? And the answer is obviously 3. So 3 is going to go in our y table here, and I was forgetting to follow along with my camera, but you can see the t-chart right now. So we have 1, 0, 2, 1, 4, 2, and 8, 3, and we're just going to graph those on our graph right here. So we got 1, 2, 3, 4, 5, 6, 7, 8, and we're only going to go up to 3. 1, 2, 3. So let's plug in our numbers here. So we have, up from our t-chart, we got 1, 0. So we'll put that right down here, 1, 0. And then we have, I'm going to move the light here a little bit so there's less shadow. At least I hope there's less shadow. And then we go to 2, 1. So here we are at 2, 1. So down here, 2, 1. And then we have 4, 2. So it's 1, 2, 3, 4, up 2. And lastly, we have 8, 3. So we go over to 8 and up to 3. And we have the beginning of our curve here. And it goes backwards like this. And you can see that it looks kind of like the square root curve. But what I'm going to do here, and in the interest of saving some time, I'm not going to talk about the fractions and so on and so forth. But I'm going to extend this curve down this way because this is where log curves go. And you can see that just like the rational functions we talked about earlier, this has an asymptote. And the asymptote here is on the y-axis. The y-axis acts as an asymptote. So here is log base 2 of x. And in fact, all log functions have this same shape. This is a new parent function for you to know. And like all other parent functions, we're just going to move this shape around. We're just going to move the shape around. We're going to move it up or down or right or left, or we're going to reflect it over the x-axis, flip it upside down, or we're going to reflect it over the y-axis. In other words, flip it over to the left. And so that's what we're going to do next. We're going to do our transformations of this particular shape here. So you're going to see this shape, and it's just going to keep moving around, up or down, right or left. So again, I move on to my transformation of my clipboard, and move that sheet out of the way, and move on to transformations. So we're going to do some transformations, and I just want to quickly remind you about how this goes. When we are adding or subtracting a number inside the function, that means we move right or left. Remember again, when you're adding or subtracting a number inside the function, it's right or left. When you add or subtract a number outside the function, it's up or down. And our other major transformation is if we put a negative sign in front of the function, it flips the function upside down. So I'm just going to write upside down. So remember, a negative sign outside the function flips the function upside down. So let's use those transformations that we've done many times throughout the year to make sketches of our log graph. And so here we have y equals log base 2 of x minus 1. The x minus 1 just says move the graph to the right 1. So I'm just going to make my little xy coordinate plane here. And just like we did with our rational functions, we're supposed to move the graph to the right 1. So I'm going to draw in a new y-axis moved over to the right 1. So there it is. And then my parent function is just going to be graphed where it usually is. So I'm going to graph this over one space to the right and use the same basic shape as we just had just a moment ago. And there it is. There's our asymptote, and there's our place where we hit the x-axis right there at 1, 0. And there is our first sketch of a logarithmic function. We just moved it to the right 1 space. And now we're going to do the same kind of thing with the next function. And here we have log base 5 of x minus 3 plus 4. And it doesn't matter whether it's log base 5 or log base 2 or log base 10 or natural log. They all have the same basic shape, and the shape looks like that. The different log numbers here, the different log bases, just make this shape a little steeper or a little less steep, but I'm not concerned about that right now. We're just making rough sketches. So we are going to make our sketch of log base 5 of x minus 3 plus 4. So we're going to move to the right 3. Remember, we want to make that 0. And we're going to move up 4. So we're going to move both of our axes. We're going to move to the right 3 and up 4. So I first draw in my regular xy coordinate plane. And then I put on here 1, 2, 3 to the right, 1, 2, 3, 4 up. And I draw in my new axes. So here's my new y-axis right here, and my new x-axis. I think the red is showing up okay on the camera. And then I just draw in my graph in the same basic shape. And so from the origin, which is our new origin is right here, we go over one space, because that's where our graph always crosses the x-axis, whether it's the new one or the old one. and we go with our asymptotic approach to the y-axis, and we draw the rest of our graph. And there it is. It's just the same graph, moved over to the right and up. Over right 3 and up 4. And our last graph is a little more complicated, but not very much more complicated. I just stuck a negative sign in front, which means we're just going to reflect it over the x-axis. And so the order of our transformations is we're going to move left 2, down 1, and then we're going to flip it in the x direction, or we're going to reflect it over the x. So let's make our little xy coordinate plane here, and we're going to do 1, 2, 3. Probably didn't need to go in that direction. 1, 2, 3. 1, 2, 3. 1, 2, 3. Alright, and so we are going to move left 2 and down 1. So I'm going to put in my new axes. Left 2 and down 1. And we're going to make sure that we flip this graph in the direction of the x-axis. So instead of going up like this, we're going down like this. And again, we're going to go one space over. Here's our origin. We're going to go one space over from the origin and make sure we go through there. And this time we're going through upside down. And there is our last function that we're going to sketch. And again, this should all be quite familiar to you because we've done these transformations many, many times. Alright, speaking of transformations, I'm going to transform onto the next sheet of paper. Alright, now the next thing we're going to do is we're going to solve some simple log equations. And here is our first simple log equation. It is log base 2 of 4x plus 3 equals log base 2 of 7x plus 1. And you'll notice that these are the same. Log base 2, log base 2. So just as long as the log and the base are the same, then all we need to do is make this piece equal to this piece, just like we did last lesson when we did our exponential things. We had to make the bases the same. These are already going to be the same. So then we just make our equation, which is 4x plus 3 equals 7x plus 1. And then we just do our algebra 1 tricks here. So we subtract 4x on both sides and subtract 1. So I get 3x on this side and 2 over there. Divide by 3, and so we get x equals 2/3. And that was easy enough. And the last one of this type, because there's only two, this is a pretty simple thing to do here. The last one is a bit of a quadratic one, and that's okay because we're all good at solving quadratics by now. And so it is the natural log of x squared plus 3x plus 4 equals the natural log of 2. And you'll notice that it's the same base. This is a log base e, it's the same thing. So really all we need to do is just set this equal to this. So we have x squared plus 3x plus 4 equals 2. And then we just subtract 2 from both sides, and we get x squared plus 3x plus 2 equals 0. And we factor that, and we have x plus 2 times x plus 1 equals 0, and our solutions are -2 and -1. And of course we would check both of these solutions into here to make sure that we don't get anything negative inside here, and I think that we're not going to, so we'll just check them though to make sure. So -2 squared is 4, minus 6 is -2, plus 4 is +2. That one's good. And we check the -1 in here. So -1 squared is 1, minus 3 is -2, plus 4 is +2, so the -1 also works just fine. Alright, and so here's the last bit of our lesson right here, the last thing we're going to do. And I just want to introduce to you the laws of, I wanted to introduce to you the laws of logarithms, But before I do that, I want to remind you of this most important point here, which is logs are exponents. So let's take a look at our first law right here. And it says here the log of a times b. Well, we know from Algebra 1 that when we are multiplying two things that involve exponents, we have to add their exponents. And so log of a is an exponent, log of b is an exponent. So the log of a times b is really going to be the log of a plus the log of b. Because remember, logs are exponents, and whenever you multiply two things, you have to add the exponents. So we're adding log of a plus log of b because those are both exponents. And by the same kind of reasoning, we have log of a divided by b, so obviously that means we're going to subtract the exponents. So log of a minus the log of b. That's rule number 2. And lastly, rule number 3. Again, remembering that log of a is an exponent. And here we have b, which is also an exponent. So what we really have going on here is a power to a power. And we know that when we have a power to a power, such as x squared to the third power, we multiply those two exponents. So log a is an exponent, b is an exponent. So when we have a power to a power, we multiply the exponents. So we're going to write b times, that's a times, log a. So these are our 3 rules. When you multiply things, you add their exponents, so log a plus log b. When you divide things, you subtract their exponents, log a minus log b. And when you raise a power to a power, you multiply those two exponents, b times log a. So we're going to use these laws and properties to expand some expressions. And so here's our very first one right here. We're going to expand our log expressions. So our first problem is log base 3 of 2 times x. And as we just said, when we multiply things, we have to add their exponents. So if we expand this out, this is really just going to become log base 3 of 2 plus log base 3 of x. And that's it. Just expanding that out using our first law. And the same thing applies here in b. This is log base 9 of 8 divided by x. So that's simply just going to be log base 9 of 8 minus log base 9 of x. Just subtracting those exponents. Very simple stuff involving the laws of logarithms. And now here we have law number 3, and so it says log base 6 of x to the 7th. We have a power to a power, that means we multiply the exponents, and so here it is, 7, that's an exponent, times log base 6 of x. 7 log base 6 of x. Just multiplying the two exponents, there it is. Another way to think about this is we're just going to bring the 7 down in front. That's really what's happening there. Just bringing down the exponent down in front of the log. Alright, so let's move down to part D here. We just got D, E, and F will be our last one. So natural log, again this is just a log, log base E. So natural log of the cube root of x is really the same as the natural log of x to the 1/3 power. But as we just realized in the previous problem, all we need to do is bring the exponent down in front. And so we have 1/3 ln x. And we're done with that problem. Easy stuff. Alright, things get a little more complicated with this one. And here, the way I think of this is I see an x times another thing, x plus 3 squared, or another expression. So I'm going to use the idea that this is a multiplication, and I'm going to expand that multiplication into an addition piece. So I got the natural log of x, ln x. Remember, when we multiply, we add the things. So now it's going to be the natural log of x plus 3 squared. And really, we're almost done. And then we see that we have an exponent here. So the natural log of something to a power just means bring that exponent down in front. So our final step here is just ln x plus 2 ln of x plus 3. Now sometimes people fall into the trap here of saying, oh, I see, ln of x plus 3, that's just the natural log of x plus the natural log of 3. And that's not true, remember. It's the natural log of x times 3 that we can expand. Multiplied things, you add the exponents. So we're just done right here with this problem. And that leaves us with one problem left to do. And it looks kind of nasty, but it really isn't all that bad at all. Alright, so here is again what I see. I see a division right here, so that's where I'm going to start. I know there's a multiplication up here, but this is really multiplied, but this is within the fraction, so I'm going to deal with the biggest part that I can first, which is actually really there's the bottom part of the fraction. This part applies to everything up here, so I'm going to deal with it first. So when things are divided, we subtract the exponents. So that means we're going to have the natural log of x squared times the cube root of y minus ln z to the fourth. Already it's looking better because now everything's on one line instead of in a fraction. And so I'm just going to go a little further here. I see that things are being multiplied, and that's fine. When things are multiplied, we just need to add them. So that means we have ln of x squared plus ln of, watch this, I'm going to write this as y to the 1/3 power, did two steps at once there, minus ln z to the fourth. And then the last thing we need to do is just take all of these exponents and bring them down in the front. So all we're going to do is our last step, and then we'll be done, fully expanded. So we'll have 2 ln x plus 1/3 ln y minus 4 ln z. And there is your final answer to your final problem there. The assignment is up on the board, and your teacher will also have that. If you have any questions, don't hesitate to ask Lisa if she's there, because I'm sure she would love to help you out. Hope you have a great time with this assignment, and I will see you next week. Thanks.